Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems and today we will see about deadlocks. So, the learning objectives for today's class is that we learn about what deadlocks are, we learn about how deadlocks can be prevented and how we can avoid deadlocks. So, in the last module we saw what is meant by a deadlock. That is, deadlocks are possible when you have resources which are shared between concurrent processes. So, when you have shared resources, many processes may have to access those resources, and it is possible for deadlocks when there are waiting processes and sharing happening in parallel. So, and we also saw that there is a system, any system can be represented using a resource allocation graph. And we also saw that in a resource allocation graph, if you are looking for cycles and if you find cycles, it is possible to have a deadlock, there may be a deadlock. So, resource allocation graph can be used for checking for deadlocks. And then we saw about the different ways in which you can handle deadlocks. So, we saw that you can prevent deadlocks, you can avoid deadlocks, or you can let deadlocks to happen in a system, and then you can try and detect the deadlocks and then recover from the deadlocks. Or the worst case is that you do not bother about what happens in the system at all, you just let deadlocks to happen. In due course of time the system performance will deteriorate, and then you try to restart the system manually so that you can kill all the processes and you can come out of the deadlock situation. So, now we will first learn about this deadlock prevention. So, why do you need to prevent deadlocks? So, you need to ensure that deadlocks do not happen in the system at all. So, for that you need to ensure that the 4 necessary conditions that we are seen for deadlock to happen in a system. That is, the conditions are mutual exclusion, hold and wait, no preemption and circular wait. And at least if you are able to avoid one of these 4 conditions, if you are able to prevent one of these 4 conditions from happening, then you will ensure that deadlocks do not happen in the system. So, we will see now each of these 4 conditions and see how we can avoid or prevent each of those conditions. So, first is mutual exclusion, and if you have shareable resources, so if you have a resource which can be shared by many processes at a particular time, then there is no need for mutual exclusion. But if you have resources which are non-shareable, then it is a mutual exclusion will hold, it must hold. That is, if you have a resource which cannot be shared by many processes at the same time, then the resource can be used by only one process at a particular time, and hence a mutual exclusion will hold. So, if you have a non-shareable resource, a resource which cannot be shared by many processes, then you cannot deny mutual exclusion condition, or you cannot prevent deadlocks by denying mutual exclusion condition. So, this cannot be always prevented when you have non-shareable resources. So, we will look at the next condition, that is hold and wait, and we will see how we can prevent this hold and wait to happen. So, this must guarantee that whenever a process requires a resource, it does not hold any other resources. So, if that is possible, then this hold and wait condition will not occur. So, when a process wants a resource, it should not be holding any resource. So, how do we ensure this? So, for this, the first solution is that the process has to request all the resources before it begins execution. So, before it does any other job, so whatever resource it will need for its entire execution, it will have to request beforehand and get everything, and only then it should start executing. So, for this what should be done is that to implement this, the system calls that are requesting the resources should be happening before the other system calls in that particular process, or the system calls requesting resources should precede all other system calls. And the next solution for not allowing this hold and wait is allow process to request resources only when the process has none. So, that is, say a process has got some resources and it is holding those resources and is asking for other resources. It should not do it that way. What it should do, if it is not able to get other resources, it should release the resources and then try to get everything in one shot. Say for example, you have this process copying data from a tape drive to a disk file, and then it will sort that file in the disk, and then it will print the results to a printer. So, this has to be done by a process. And what are the resources that need to be used here? It needs to have the tape drive, it needs to have the disk, it needs to have the printer. So, the resources are tape drive, disk and printer. All the three resources should be used by this process. So, now the first solution to not having a hold and wait is that it needs to acquire all the three resources beforehand before it starts with any other execution. So, even before starting any execution, it needs to get the tape drive, it needs to get the disk, it needs to get the printer. Only if the process gets all the three devices, then it can continue with the execution. This is one way. The other is it can get the tape drive and the disk, it can do the copying from the tape drive to the disk, then it will relinquish, it will release both the tape drive and the disk, and then it will get the disk and the printer and then continue with this execution. This is the next solution. But if you look at this two solutions, both the solutions, we can see that there is low resource utilization. Why you have low resource utilization? Because say in the first case, you are holding all the three resources beforehand and you are using only the tape drive and the disk at a particular time. At that time, the printer is just free, it is not being utilized at all. And after that, then you are copying from the disk to the printer, you are printing the contents from the disk to the printer, you are utilizing only the disk and the printer, you are not using the tape drive and hence the tape drive is not utilized. And you have less resource utilization, the resources are not utilized properly. And it is also possible to have starvation. Why starvation? Because say you have some resource which needs to be used by many processes, say you have a printer which needs to be used by many processes, and then if you have been, if one process keeps on using it, it is holding it and it is not assigned, releasing to other process, then the other process may have to wait for a long amount of time. So, starvation is also possible. But with these two solutions, you can ensure that hold and wait does not happen in a system. And the next is to get rid of this condition of no preemption. So, no preemption should not be there, which means that you should allow preemption. So, preemption again you got two cases. One is the process by itself releasing the resources or preempting the resources. The second is somebody else preempting the resources from the process. So, we will look at those. So, if a process that is holding some resources, it is requesting another resource that cannot be immediately given to it, then whatever it is currently holding should also be released. So, in this case, the process by itself is preempting the resources it is holding. So, it has got, say for example, two resources in the same example that you had seen earlier. Say it has got, say the tape drive and the disk, and it is not able to get the printer, it wants the printer also to continue. The printer it is not able to get, and then what should it do? If it is not able to get the printer, it will release the tape drive and the disk also, so that maybe somebody else can use it, and finally this can continue after some amount of time. It will not lead to a deadlock, maybe it will delay the time for which, the time at which it will complete, but it may not lead to a deadlock. And these preempted resources are added to a list of resources for which the process is waiting. And the process will be restarted only when it can regain its old resources as well as the new one that it is requesting. So, it relinquishes the tape drive and the disk, and all are added to this pool of available resources, and it can continue when it gets both all the three, the tape drive, the disk and the printer. This is one solution. And then you have another solution. If a process is requesting for resources, you check if the resources are available. If they are available, you allocate them. If it is not available, then you need to check if the resource is currently allocated to some other process which is waiting. So, in that case, what is done is that you preempt the resources from that waiting process and you use and continue. So, in the solution, the process by itself is not releasing the resources it has got. It is trying to find out if some other process has got the resources that it is holding, and that process, the some other process, should be a waiting process. So, if the resources that this process needs is currently held by another waiting process, then remove the resources from that process or preempt the resource from that process and this process continue. So, in this case also you can come out of this no preemption situation. So, here you allow preemption and hence you try to prevent deadlocks. And if it is not possible, nothing is possible, the process will wait anyway. If it is not able to get some other process which is waiting and holding resources, then this process will have to wait naturally. And then the next situation is circular wait. In circular wait, what is done is the resource types are ordered. They are ordered by giving some number. Okay. And when process is requesting for resources, they will request for the resources only in this particular order. Say for example, say you have got resources R1, R2, etc., Rn, and there are n number of resource types present in the system. And what you try to do for each resource type, you try and assign a number. So, this function f assigns a number for each resource and that n is an integer number. Look at this example. You have a tape drive. The tape drive is assigned a number equal to 1 and disk drive is assigned a number equal to 5 and printer is assigned a number equal to 12. Now, when any process wants say tape drive, disk drive and printer, it should only request for the resources in the order of tape drive first, next disk drive and then third printer. The number that is being assigned to the resource types are in increasing order 1, 5 and then 12. So, request for resources only in this order. So, only if a process gets the tape drive, then it will request for the disk drive. Okay. So, after requesting Ri, it can request Rj only if Rj's f of Rj is greater than f of Ra if you are doing notations. So, the example as I told you is only get disk drive and only then you get the printer. For several instances of the same resource type, a single request for all of them should be issued. Say you need say 2 disk drives, or if you need 2 tape drives, you need to get both the tape drives first and then only you need to request for the disk drive. So, if you need multiple 2 instances of resource type tape drive, then you need to get them together in one shot. Second protocol is that when an instance of Rj is to be got by a process, to be acquired by a process, and it is holding some instances of Ri, but the number of Ra is greater than or equal to the number of Rj. So, only after it gets Rj, it should be able to get Ri. But now it is holding some instances of Ri. Then in that case, it should release all the instances of Ra that it is currently holding and then it should try and get the instances of Rj. That is, it strictly try to get the instances of the resources only in an in that order of enumeration. Suppose we will approve this example, prove that this condition is enough or this enumeration is enough for circular wait not to happen in a system. We will prove that by contradiction. Suppose a circular wait exists in a system, then you will have these processes P0, P1, P2 etc. up to Pn are the resources that are involved in the circular wait. That is, you have process Pi that is waiting for by a resource held by process Pi plus 1. So, look at this, you have process P1 and P1 is waiting for a resource held by P2, P2 is waiting for resource held by P3 and P3 is waiting for resource held by P4 and P4 is waiting for a resource held by P5 and in turn by P1. So, in this case if this exists, if such a circular wait exists, then say f of R0 should be less than f of R1, should be less than f of etc. and so on, R2 etc. and so on, and should be less than f of R0. So, if see you can see that this P1 is waiting for a resource held by P2 and P5 is waiting for a resource held by P1. Say P1 is holding R1 or R1 and P2 is holding R2. Say P5 will be waiting for R1 which is held by P1, but P1 is waiting R1 and requesting for R2. So, R1's number should be less than R2's number, that should be less than R3's number, that should be less than R4's number, that should be less than R5's number and that should be less than R1's number. So, this P5 cannot request for R1 because the number of R1 is less than the number of R5, P5 is holding R5. So, such a kind of a situation cannot happen in a system. You cannot have a circular wait in a system. So, this is impossible and hence you ensure that circular wait does not happen in a system. So, we have seen that deadlock can be prevented in a system by ensuring that all these three, at least one of these three conditions is not satisfied, say mutual exclusion, hold and wait, no preemption and then circular wait. Mutual exclusion we cannot completely remove because you may have non-shareable resources, but hold and wait, no preemption and circular wait can be prevented. And next we will see deadlock avoidance, how to avoid deadlocks in a system. So, to avoid deadlocks, the system needs to know beforehand what will be the requests for each and every process. So, each and every process will have to tell beforehand that this is the set of resources I am planning to get during my entire execution. So, the system will maintain all this information about all the processes in the system, and whenever one process is requesting for an instance of a resource, it will look into all this information that is got earlier, and then based on that information it will decide whether it can satisfy the request that is currently come from a process. So, this is the simplest and most useful model and requires that each process declares the maximum number of resources of each type that it may need. And for any request, it will decide if the request can be satisfied immediately or it should wait based on the information that it has got. And this deadlock avoidance algorithm, it will dynamically examine the resource allocation state to ensure that there can never be a circular wait condition. And this you got something called a term called a state, the resource allocation state. It is actually defined as the number of available and allocated resources and the maximum demand of each of the process. So, at a particular time you define the state of a system by whatever is currently available and whatever is currently allocated and what is the maximum demand of all the processes. Now, so in a deadlock avoidance algorithm, you first need to ensure that the system is in a safe state or not. So, what is meant by a safe state? So, when a process is requesting for an available resource, the resource is available and the process is requesting for that resource, the system should decide if this resource which is available can be immediately allocated to the process. If it is allocated, will the system still remain in a safe state or not? So, the state is safe if the system can allocate resources to all the processes in the system in some order and still it can avoid a deadlock. So, whenever the request comes, it tries to find out if the system is in a safe state, that is it tries to find out if resources can be allocated to all the processes in some order so that the deadlocks are avoided. So, system is in a safe state if there exists a safe sequence for all the processes. So, what is meant by a safe sequence? You have processes P1, P2 etc. up to Pn in the system and the sequence, that is P1 after P2 etc. after etc. up to Pn is called safe sequence if for each of these processes the resources that each of these processes can request in future can be satisfied with the resources that are currently available and with all the resources that are held by the other process. Say P2 is making a request, then P2's request can be satisfied with the currently available resources, free resources, and with the resources that are held by P1, P3 etc. up to Pn. So, if Pi resource needs are not immediately available, then Pi will have to wait until all other Pj has to be finished. And when Pj is finished, Pi will get the resources, execute, and then it will return the resources whatever it has got also, and then it will terminate. So, when Pi is terminating, the next process can obtain the resources from this process and so on. So, here you can see that there is a sequence in which resources can be used. So, that sequence is called this safe sequence. That is, you have process Pi, then after Pi finishes, the next process Pi plus 1, then Pi plus 2 etc. can use, and they can continue without getting into a deadlock. So, some facts. So, if there is no safe sequence, then it means that the system is unsafe. If a system is in the safe state, then there is no deadlocks. Then if the system is in an unsafe state, then there is a possibility of a deadlock in the system. But when you are trying to avoid deadlocks, then it ensures that the system will never enter an unsafe state. So, if you are trying to devise an algorithm for avoidance of deadlocks, then that should ensure that the system will never enter an unsafe state. So, here just a diagram that shows a safe, unsafe and deadlock state here. So, you have deadlock state, unsafe state. Mostly the system is in a safe state, but if it's unsafe, that is the possibility of deadlock. So, unsafe does not mean it is always deadlock, there is a possibility of deadlock. So, look at this example to see what safe and unsafe states are. Say you have 12 magnetic tape drives totally available, and there are 3 processes P0, P1 and P2. And the maximum need and the current need for each process is shown. You have process P0 which needs a maximum of 10 tape drives, and the current needs is 5 tape drives, and currently it is using 5, and 5 tape drives it will request in future. And for P1 currently it is using 2 tape drives and it will request for 2 more in the future. And P2 is currently using 2 and it will request for 7 more in the future. So, currently how many tape drives are allocated? 5 plus 2 plus 2, 9 tape drives are currently allocated out of the total 12 tape drives. So, how many are free? You have 3 tape drives which are free. Now, how do we allocate to the processes the future request of each of the processes such that the system will remain in a safe state? So, I repeat again, you got 3 tape drives which are free. P0 in future will need 5 more, P1 will need 2 more and P2 will need 7 more. So, the future need of P0 which is 5 more cannot be satisfied with just 3. The future need of P2 which needs 7 more cannot be satisfied with just 3. Only the future need of P1 can be satisfied with just 3. That is, the future need of P1 is 2 which can be satisfied with the 3 that we have. So, if we give the 2 out of the 3 to process P1 first, then P1's future need will be fully satisfied. So, P1 gets its 2 more tape drives. So, it can finish off its execution, it will not get into a deadlock at all. And after finishing execution, P1 will release all the 4, the 2 that is currently having, the 2 more that we allocate now. So, the 4 will be there for P1 and P1 will release all the 4. We have 4 tape drives that are freed by process P1 and 1 that is currently available. So, we have 5 tape drives that are free. So, this 5 tape drives which are free can be given to process P0 because P0 in future will need only 5 tape drives. So, this 5 tape drives can satisfy the request of process P0. So, when process P0 finishes off using this 5 tape drives, it will release all the 5 that it has already having and the 5 that is getting now. So, all the 10 will be released. So, we will have 10 tape drives that are free, and with the 10 tape drives that are free, we can satisfy the request of P2 which will need 7 more. So, if you are trying to assign in this order, that is if you are trying to assign for P1 first and then P0 and then P2, you can see that the system will not get into a deadlock situation at all. So, the system will be safe if it is being assigned resources in the order of P1 first, P0 and then P2. So, this order P0, P1, P0 and then P2 is called a safe sequence in the system. Suppose you have this current situation, and then if you have P2 which is requesting and is allocated one more tape drive. P2 is requesting for one more tape drive and if it is allocated. So, what happens now? So, P2 requests for one more and you allocate one more. So, P2's current need, it is using 2, you allocate one more and becomes 3. So, P2's future need will become 6. But the number of free tape drives available will now become 7 plus 3, 10 is gone, only 2 are available. Okay. So, then what happens? Only 2 will be available, and then what happens with the remaining resources? How do we satisfy the needs of the other process? Will the system be in a safe state or will the system go to an unsafe state? So, currently as of now we have seen that if the order P1, P0, P2 is followed, then the system can be in a safe state. But now the system may not be in a safe state, it may move to an unsafe state. So, it is possible for a system to go from a safe state to an unsafe state. So, summary of what we have learnt in this module. We learned that deadlocks can be prevented. And how do we prevent deadlocks? By ensuring that mutual exclusion, hold and wait, no preemption and circular wait do not happen in a system, and then we can prevent deadlocks. And then we saw that with prior knowledge about all the requests, deadlocks can be avoided. So, the references, acknowledgement. Thank you.